Do you have any question? Or could you go through the lecture, the last lecture that I posted?
So not yet, sir.
Not yet. Okay. Anyone else? Okay, if you haven't gone through, then okay, there might be some confusions in today's lecture also for you. Because it is actually the continuation from the last lecture that I posted in the recorded version of which I posted in the Google Classroom. Okay, but before I proceed, for today's new part, let me have a quick recap on whatever I covered actually in the last lecture. So I introduced the Parkes transformation. Before introducing the Parkes transformation, if you remember, we talked about the flux linkages for the stator three-phase windings and the flux linkages for the rotor three-phase windings. And again, because we can clearly see that from these matrices, especially this part, that is actually the LSR, because this inductance is actually the mutual inductance representing the coupling between the stator and the rotor coils. So this should be LSS, the first block. The second block should be LSR, and we can clearly see from here the presence of the theta angle. Okay, so that means even under steady state condition, because of the presence of these theta angles over here, because theta would be continuously increasing with respect to time, even under a steady state condition. So this is a problem that we also encountered while we discussed the synchronous machine modeling. So similar kind of problem arises here. And if you can recall correctly, that we also introduced the Parkes transformation concept in case of the synchronous machine for the same problem. So similarly here also, we are going to introduce the Parkes transformation matrix. But there is a little difference between the Parkes transformation matrix that we introduced there for the synchronous machine and that on those which we are going to introduce here. Okay, so in summary, we are going to have two different Parkes transformation matrices, and of course, along with their corresponding inverse matrices. So in short, you will find the detail in the recorded version of the last lecture that I posted, but I'm giving you just a quick recap. So in short, if you can see the first one over here, this Parkes transformation is basically related with the stator quantities. Okay, so T is the transformation matrix. DQ0 stands for the DQ0 frame, and S stands for the stator quantities. Similarly, T DQ0R at the bottom over here stands for T is the transformation matrix. DQ0 is the frame where we are going to, and R is the rotor. So our initial frame of reference is ABC, the three-phase. So from ABC, this is the stator because all are small letters. So this small ABC represents the stator quantities, stator. From here, we are going to, after transformation, we are going to get DQ0 stator. These are for the stator quantities. And for this one, at the bottom, we are going to have capital ABC, and that is actually the rotor quantities. And then from there on, we are going to reach also the DQ0. So this DQ0 and this DQ0 are the common frame, but these stator ABC and the rotor ABC are different frames, different three-phase quantities. So this is also the rotor, but now in the DQ0 frame. So where is the difference? The first matrix is exactly the same as the one that we experienced while we used this concept for the synchronous machine. So if you go through each of the elements present in the matrices, the 9 elements that we have, if we start with the constant term, of course, as we discussed earlier, we can have different choices for K1 and K2. These are the constants. So either we will have a 2 by 3 and 1 by 2, this combination for K1 and K2, or we may also have a different choice like square root of 2 by 3 and 1 upon square root of 2. So this is another different set of choice. So in this case, we are choosing the first one over here, that is 2 by 3 for K1. So this is our K1. And for 1/2, this is our K2. So this is the K2. So if you look closely at each of the elements, these all the other elements are exactly the same that we found for the parts transformation matrix used for the synchronous machine derivation or the synchronous machine modeling part. Okay, so however, for the rotor part, we have a little different entries. Okay, where is the difference? The difference lies in the angular speed. So you can clearly see the differences. Instead of this omega s over here, we have omega s minus omega r. Similarly, this omega s, instead of that, we have omega s minus omega r. And similar kind of observation can be made for each of the entries. Other than that, most of the entries are actually identical. So if you simply, let's say this is angular speed within the bracket, then the first element 1 for t dq0s, it is cosine some angular speed value multiplied by t. So similarly here we have the cosine, then some angular speed multiplied by t. Second one, again, some omega st, some angular speed multiplied by t minus 120 degree. So here also omega s minus omega, this is some angular speed multiplied by t minus 120 degree. So other than the angular speed entries, all the other elements looks same. So the main difference lies between this parts transformation matrix and this parts transformation matrix is in the entries or in the values of this angular speed. So why are they different? So let me give you a quick review on that. So the first matrix, the top one, T dq0s, it is actually helping us to transform the ABC frame quantities, small ABC, that is the stator quantities, to the dq0 quantities. Okay, so dq0 quantities, shouldn't write stator here. So this is dq0 quantities. This is also dq0 quantities. Okay, this is a different frame. So we start from some stator frame or the stationary frame. So remember the ABC coils, these are stationary. So these are stationary in space. So if you want to represent them in terms of speed, their speed should be 0. Now, what was the speed of the dq0 frame? Anyone? For the induction machine? Can anyone recall correctly and quickly? What was the speed of the dq0 frame? Okay, if we go back quickly to slide number 5. Okay, can you identify what is the speed of the dq axis or dq frame from this diagram?
Omega
from this
is
diagram, what should be the speed of dq0 frame? Stator frame is stationary. Okay, stator frame is stationary. That means these a axis, small a axis, small b axis, and small c axis, these are stationary. So they remain unmoved. So their speed, let's say omega equals to 0. What is the speed here for dq0 frame?
Below synchronous speed.
Sorry? A little louder, please.
Below synchronous speed. Rotor speed.
It's not clear. Okay, I will come to that later on. Okay, again, what is the speed of the rotor frame?
Synchronous speed is from below synchronous speed.
Okay, so dq0 is the synchronous speed. So let's write it omega synchronous or omega s, all the same. Thank you. What about the rotor frame? Omega r. So this is omega r. What about dq0? It's the same as this, omega synchronous or omega s. So you can see whenever we are using the Parkes transformation matrix, the angular velocity that is present there is simply nothing but the difference between this value over here and this value over here. In other words, we can write the relative speed between this frame and this frame is nothing but omega s minus 0 and that is nothing but omega s. So this is the relative speed so this is the relative speed between this dq0 frame and this stator or stationary frame. And you will see that in the t dq0s transformation, everywhere you will come up with this entry omega s. Similar observation now for transforming the rotor ABC quantities into the dq0 frame. What we have to do, simply you have to write omega s, the relative speed, omega s minus omega r. So in all the entries in the Parkes transformation matrix for t dq0 r, we are going to get this. So this is the simple explanation for the difference between these two matrices. Okay, any question? No question. Okay, so let's proceed. So in this manner, we are going to introduce basically two different Parkes transformation matrices for the derivation for the modeling for three-phase induction machine. So these are presented here in equation 6a and 6b respectively. And then we applied those Parkes transformation for obtaining the dq0 frame flux linkage for the stator, which are listed here, lambda d, lambda q, lambda 0. S stands for the stator here. And similarly for the rotor, lambda dr, lambda qr, and lambda 0r, we get equation 7b. And while deriving this, these are some of the simplifying notations that you may use, so that ultimately you will get exactly the same entries which are appearing here for 7a as well as for 7b. So from where actually we are getting these 7a and 7b, so you have to go to the flux linkage equation for this 7a. You are applying the Parkes transformation matrix on this. Okay. So now can we tell which of the Parkes transformation matrix would be required here? This is an ABC frame. So should we use t dq0s or t dq0r? This is an ABC frame. We want lambda ds, lambda qs, and lambda 0s. Okay. So we need to use t dq0s. Okay, got it? Similarly here, what we need to do, this is an ABC frame, but a small ABC. So this is again in stator quantities. So we want actually IDS, IQS, and I0S. So similarly here, we need to use TDQ0S. This is a transformation. This is an inductance matrix. What about this? This is an ABC frame, and these are the rotor currents. So to transform it into IDR, IQR, and I0R, we need to use TDQ0R. So these are some of the issues that you have to be careful about while you are transforming from this equation 4, while you are going from this equation 4 to equation 7a. Okay, this is for the stator winding flux linkage. Similarly here for the rotor winding flux linkage, for the first entry, this is in the rotor frame, lambda a, b, c, all capital. So you need to use TDQ0R. Then this entry, this vector is for the stator ABC. So you need to use TDQ0S. And this entry is for the rotor. So you have to use TDQ0R. So once you use that, then you should come up with the equations present in 7b. So thus we can get easily 7a and 7b calculations done. What about the next one? So we are done with the flux linkage expressions here in 7a and 7b, but similarly we also have some voltage expressions. Okay, we applied the KVLs for each of the three phases for the stator winding, phase A, phase B, and phase C. Similarly for the rotor winding, it was phase A, B, and C. So now as you can clearly see, this is ABC frame, equation 2A up to 2C. So this is for the stator. So we need to apply TDQ0S to transform it into VDS, VQS, and V0S, and so on. This will be IA, IB, IC. Again, you need to apply the TDQ0S Similarly, this is lambda A, lambda B, lambda C. You need to apply TDQ0S. For rotor winding voltage, everywhere we need to, because you can see it is all caps, V capital A up to V capital C, I capital A up to I capital C, and lambda capital A up to lambda capital C. So everywhere there are the rotor, these are the rotor variables or the quantities. All of these quantities are actually in the rotor frame. So for transformation, we need to use only the TDQ0R matrix. Okay, so once that is done, you can easily find out equation 8a and equation 8b for the stator and for the rotor respectively. Similarly, we can come up with the expression for the apparent power. And in the apparent power, you will see that there are 3 entries. The first entry, after you go through the transformation, application of the transformation matrices, then you will come up with 3 different parts of the expression for the rotor apparent power. The first part would be the rotor copper loss. You can see clearly I square R. This RR is the representation of the rotor coil resistance. So this is purely the power loss component, which is the current dependent power loss. So that is the copper loss. And only the rotor resistance is associated there. So this should be the rotor copper loss. The third part here, it is only present during the dynamic state. So you can see that this lambda d by dt term is there for both of these two. So as long as the system is in a steady state, this term would be 0. So you are left with the middle term. So first term is the loss, second term is the dynamic quantity. The middle term is interesting in a way that you can clearly see that we are actually looking for some power expression over here, okay, S rotor. So in the power expression, we can actually relate power and torque in this manner. So any power can be represented by the torque tau multiplied by omega. So you can clearly see that here we have the presence of some term where flux linkage and currents are coming in the multiplicative form. And there is some other term which represents some relative speed. So if you take omega as this, so the remaining term should be the torque. And thus you can say that this torque, this term over here, lambda I, the multiplicative terms, lambda QR IDR minus lambda DR IQR, this is nothing but some form of torque. So if you want some generalized expression for a machine where P number of poles are present, then you have to multiply this additional term over here for the generalized torque expression of an induction machine. So all these are actually covered in the last lecture in the recorded version. Also the power unitization is covered there. So power unitization is actually done just for the simplicity of your calculation, and so that you don't have to bother about the unit conversion every time. Only the power units are present throughout your system, so that you don't have to bother about the different voltage levels present throughout your system. So, and also the values, numeric values becomes pretty small, okay, near to one per unit or something like that. So basically you are scaling it for your benefit of calculation. So as you all know that per unit quantities on the per unit calculation, we need to set some base quantities at the beginning of the calculation process. So similarly, we are taking some of the base quantities as the voltage base, the current base, and the frequency base, and accordingly we are setting some other bases like the impedance base, the angular frequency base, the inductance base, the flux linkage base, the apparent power base, and the torque base. So all other required base can be calculated based upon these 3 over here. So once you are done with the base calculation, then slide number 15 shows how we can get the per unitized variables like VDS. The capital V represents now all the capital, this V, capital V, this capital I over here, capital I, all these represents now the per unit representations. Okay, so accordingly I discussed how we can get all these actually. So this is pretty simple. You take the actual quantity VDS and divide it by the corresponding base, because VDS is the voltage term, so you divide it by the base voltage and so on. IDS is a current term, so you divide it by the current term, and psi ds is a flux linkage term, so lambda ds is the actual flux linkage, so you divide by the lambda base and so on. If you look for XS, that is the inductance. So for the reactance, the inductive reactance, so you have to use the Z base and so on. And then if you get the equations, ultimately, if you try to get the equations, that is the voltage equations that we got here in slide number 12, you can see it is VDS, VQS, VDR, and VQR. And of course, the zero elements are there. So these are in actual variables. You can see a small VDS, a small VQS. So all these means these are in actual quantities. So when you make the per unitization, then you get the expressions in slide number 16 present in equation 11a up to 11d. Intentionally, the 0s, that means V0s, that is the stator zero axis component for the voltage, and rotor zero axis component for the voltage. These expressions, considering it is a balanced system, so we are actually not bothered about those two. So those two are not included. You are only seeing two from each of the circuits, two from the rotor circuit and two from the stator circuits. The zero elements are not taken into consideration further in our derivation. Okay, so what you will get now, your RS, IDS. So all these now, you see V capital, R capital, I capital, Psi capital. So all these are now in per unit form. So you get actually 4 expressions, 2 for the stator voltage and 2 for the rotor voltage. Now, while we did this, we can now clearly see that we have some form of state variable representation slowly growing up. So you can see that on this side, we have some form of state variable. So d by dt psi ds. Another state variable could be this one, d by dt psi qs, d by dt psi dr, and d by dt psi qr. Okay. So now these are the 4 equations that could be our candidate state space model variables or representations. So along with this, we can also see that there are some variables which are not actually the state variables. Okay, even if we consider that for the time being, these are the state variables. Just looking at these 4 equations, psi ds, psi qs, psi dr, and psi qr, then if we start looking closely into these expressions, VDS is not one of the state variables. It is not listed here. IDS is not a state variable. RS is of course a constant. It's a stator winding resistance in per unit, so it's a constant. Omega base is the base angular frequency, it's a constant. Psi QS is of course listed here, so there's no problem with that. But still we have to deal with this VDS, IDS, VQS, IQS, VDR, IDR, and VQR, IQR. So these are the elements that are still those are still causing some problem in our state space model representation. So let's see slowly how we can get rid of those, or how we can actually express those in terms of our state variables. Okay, so then, so besides the voltage expressions, if you remember, we also had some flux linkage expressions actually. So now we per unitize those expressions. So by the flux linkage expressions, I mean the expressions present in slide number 11 in equation 7a and 7b. So these are in actual quantities, lambdas are in actual quantities, whereas psi, capital Psi, these are in per unitized form. So equation 12a to 12d, again, I should mention it here that intentionally the Psi 0s and Psi 0r, these are not listed here. Okay, we are only interested in this Psi ds, Psi qs, and Psi dr and Psi qr. Okay, so these are the algebraic expressions for the 4 flux linkages. Algebraic expression, you don't find any derivatives present here in this set of equation 12. So these are the per unitized form of flux linkage expressions. Now if we go for simplification, remember we always look for some simplification. just to make life easy, and also based on the choice of our study. Okay, the choice of our study. In this case, we are always interested in the small disturbance stability. For this course, this was our target: small disturbance stability or low frequency oscillation problem, LFO problem. So low frequency oscillation problem actually means it is from 0.1 hertz to 2 hertz. This is the range of frequency that we are interested on. So any frequency which is very near to the power frequency, power line frequency is 50 hertz or 60 hertz. Any frequency which lies in that zone, we are not going to capture that in our modeling. Okay, we may neglect them. For example, if we were interested in some analysis known as subsynchronous resonance or some supersynchronous phenomena, okay, subsynchronous resonance or supersynchronous phenomena, in those cases we had to include this thing, okay, that we are neglecting here. So what we are neglecting here, so similar to the synchronous machine simplification process, to start with the simplification process, we are going to neglect the fast stator transients. This fast means it is the value of this transient, means this one, d psi ds by dt. So if I write it here, so the stator flux linkage dynamics, d psi ds over dt and d psi qs over dt, it is pretty fast compared to the frequency zone of our interest or frequency range of our interest. However, if we were analyzing this SSR thing, the subsynchronous resonance or the supersynchronous resonance, where the frequency lies in this range, if your, let's say 50 hertz is your power line frequency, then subsynchronous resonance phenomena occurs somewhere around 49 hertz, 45 hertz, or something like that. Supersynchronous resonance occurs around 51 hertz or something like that. So in those cases, we cannot assume these to be neglected, these two. However, for the LFO problem or the small disturbance stability problem, our frequency of interest is completely different. It lies in the very small frequency range. So thus, we are not going to include these dynamics in our model. We can neglect them. So with this logic, we are actually neglecting the d psi ds by dt and d psi qs by dt, which were present in equation 11a and 11b. So if we neglect these, we will be simply left with vds equals rs ids minus psi qs. And again, if we neglect this, simply we will get vqs equals rs iqs plus psi ds. So this is what we have written in equation 13a and 13b. So this is simplification number 1, step number 1. There are a few more steps for simplification, so let's go through those slowly. Now, as I said, there are some presence of i's, okay, idr, iqr, ids, iqs, which are not some of the state variables or some of the variables where d by dt terms are appearing. So what we can do, we can slowly try and erase them, replace them by their equivalent expressions. Okay, so in doing that, what we can do, we can simply use the expressions for psi dr. So remember what was psi dr. So let's go to the flux linkage expressions. So this is psi dr. So from this psi dr, what we will do, so from here we can easily write idr equals psi dr minus xm ids divided by xr. Similarly, from this one, we can write iqr equals psi qr minus xm iqs divided by xr. So in doing that, what we can achieve by doing that is simply we can get rid of idr and iq. Two of the current which are associated with the rotor circuit, we can get rid of that. Okay. So instead of those currents, what we will get some psi in the rotor circuit, the D component of that, the Q component of psi in the rotor circuit, and some stator currents, D component and Q component. Okay. So instead of these two, we will use this and this. So where we will use this, we can clearly see in 12A, we can replace IDR by this one. In 12B, we can replace IQR by this one. So this is one place where we can replace IDR and IQR. So what we are doing in summary, we are simply using the expressions 12C and 12D to get some equivalent expressions for IDR and IQR. And we are replacing it in equation 12A and 12B so that ultimately psi ds and psi qs can be represented in some with the help of some variables other than IDR and IQR. This is the target. This is one of the simplification that we can do by these expressions IDR and IQR over here. So let's see what else. Okay, so this is actually mentioned in this slide number 19, equation number 14A up to 14D. Okay, so you can see that psi ds is now not a function of IDR, and similarly psi qs is not a function of IQR. So interestingly, psi ds is some function of IDS. Well, some more IDS is appearing, and some function of psi dr. Psi qs is some function of IQS only. However, there is some presence of psi qr also, but no IDR and IQR. Okay. So then what we do some further simplification of 11C. Okay, 11C. What was 11C? Let's go and check. So 11C was some voltage equations. Remember 11A and 11B already simplified by neglecting these terms. So 11A is simplified to this. 11B is simplified to this. Now we are in 11C. So in 11C, what we see on the left-hand side, we have some voltage expressions or voltage variables in the rotor circuit, D axis and Q axis. Now, what would be their numeric value? Can anyone say? Rotor circuit voltage for induction motor, what would be the numeric value of VDR and VQR? Any idea? What should be the numeric value? Shafiullah.
Yes, sir.
Can you say what should be the value of VDR and VQR?
So numeric value of VDR and VQR.
Or even don't bother about VDR, VQR. Let's say VA, VB, VC in the ABC frame. If you are confused, let me make it easier for you, all of you.
Sir.
Yes, Rahid. I mentioned it actually in the last class where we met actually.
The short circuit. It is short circuit.
Actually those are short circuited. So you will get a very small value, negligible value, probably if you take it in the DQ frame, but you can actually take it as negligible. Okay. In per unit, it would be further reduced. So because in the rotor circuit, the rotor coils are actually short circuited. Okay, so that you can have some rotor flux produced. So you actually short out the coils either through resistors or directly. If it is a squirrel cage, by manufacturer, it is shorted by end rings. If it is wound rotor, then either you use resistors for a starting torque control, or if you don't want that, then simply you have to short it. So you can see that there is no way that there will be some voltage across the terminals because the terminals are shorted. So these VDR and VQR, even after transformation, they may take some very small value, which are negligible in nature. So the first observation is that the left-hand side of 11C and 11D would be actually, can be assumed to be 0. Okay? Because of the presence of the short circuit across them. Then what else can we say? What about this one? IDR and IQR, we already know they are replacements, right? They can be replaced. Shy QR, shy DR, okay, just leave with them for the time being. And this is your state variable form, so leave with them. Okay, just leave those terms for the time being. So what we can see, this could be 0, this could be 0, and you can replace IDR and IQR. Okay, so this is actually what is done in slide number 20 at the beginning. So from 11C, this was actually VDR. So VDR is actually assumed to be 0. RR, this is IDR minus S psi QR plus 1 upon omega base D psi R over dt. The remaining terms, these two terms remain same. Then because we are looking for some state space representation, so we always like this d by dt term to be appearing on the left hand side of our equation. So we have brought it to the left hand side, and the remaining things are on the right hand side. All the things which are remaining are on the right hand side. Okay. So then what we do, we intentionally include some reactance terms, specifically this term XR over XM, and in doing that, what we see that actually the psi dr can be replaced by this term. Sorry, psi dr. Yeah, this is psi dr. The first one is psi dr. So now there is some further notational simplification. So we are introducing actually some new voltages like VQ dash and VD dash, which are nothing but some function of our flux linkages in the D axis, rotor, and flux linkage in the Q axis, rotor psi QR. So with this notational simplification, these top two, we can write psi, instead of psi dr, we can simply write psi dr equals to what? XR over XM VQ dash. So this is what is done here. So now we are not going to take the psi variables as our state variables. Instead of that, a more natural variable, a variable that is more known to us, that is in terms of voltages, okay? Rather than flux linkage taken to be the state variable, we would like to take the voltage terms or voltage variables as our state variables, voltages, currents, and all those things instead of flux linkages, just to make life easy. There's no problem even if you consider psi dr as your state variable. Just for the simplicity, we can introduce some voltage terms here instead of flux linkages, but there is no harm. We can also go with this. There's no harm with that. So here we are introducing some new notations for the voltages VQ dash and VD dash. Then accordingly, we are updating the entries. Okay, nothing special here. And then we also want to introduce some time constant terms and some new reactance terms like XS dash and TO dash. TO dash is nothing but the open circuit time constant. And remember here we are not using TDO dash or TQO dash because the D axis and Q axis air gaps are identical, okay? Uniform air gap. So all the same, TO dash for the D axis and TO dash for the Q axis should be identical. XS dash is some transient term of XS, okay? Some transient term of XS. So you can call it like stator coil reactance in the transient period, XS dash. The representation is this. So with all these four assumptions, we can develop all the lines in between, and ultimately we can come up with our desired expression over here, which is denoted by equation 15a. So now we can see that it looks quite good. We have a voltage variable VQ dash as a state variable. We have a time constant for that dynamics. Then on the right hand side, the first entry is the same state variable, so you don't have to bother. XS minus XS dash, from where it is coming. So you use this relation, XM square over XR. This is the term you are getting here. So you take XM square over XR, then you get XS minus XS dash. So this is what we have written. However, the current terms is still there, but that is the stator current dx's component. Minus S, remember S is the slip, small s, it is the slip. It is not the Laplace domain variable S, it is the slip S. So don't get confused. TO dash, it is the time constant, so this should be a constant. Omega base, it is a constant. VD dash, we will see in the next slide that VD dash would be one of our state variables. So we don't have to bother about this because it is one of the state variables. So only thing remaining would be probably IDS that we still have to manipulate or still have to play with later on. So let's see how we proceed with that. So all these steps are actually taken from 11C or started from 11C and ended up here at 15A. So we have got in state variable in terms of voltage. QX is voltage transient. Similarly, we do something with 11D. In that 11D, on the left-hand side, we had VQR. So VQR is assumed to be 0 because of the short-circuited rotor coils or rotor terminals. Then you have RR-IQR. This is IQR replaced plus S psi dr plus 1 upon omega base d psi QR by dt. So like the previous slide, here also all those 4 assumptions are listed, or simplification are listed. And using all these 4, we can reach up to this point. In between, we have some steps that are pretty straightforward. Nothing actually special about that. So this is the last equation 15b, that we come up with. And you can see now that we have VD dash as our state variable. TO dash is the same TO dash that we used in the previous slide. VD dash is the state variable, so don't have to bother. XS minus XS dash, again, we have XM square over XR. So if you take XM square over XR, you get something like XS minus XS dash, and that is appearing there. Now, still we have some current term, stator current IQS. We have to deal with it later on. STO dash, S is again the slip, and VQ dash is the state variable. So if equation 15A and equation 15B simply gives us 2 state variable expressions or 2 dynamic equations for the induction machine, 3-phase induction machine model. If we continue our derivation, so as we all know that the induction machine has its own shaft, and like the synchronous machine, it will have its own equation of motion. That means the swing equation, but now it would be for the induction machine. But before that, what we do, we simply take the torque expression TE. This capital TE means it is the per unit torque. The small TE was the actual torque expression. We divide it by the base torque. This small TE is this corresponding expression is taken from one of the previous slides. Torque base is taken from the slide where we mentioned all the base quantities. If we divide them, ultimately you come up with this expression, equation number 16, where you see that again it is some flux linkage multiplied by current. So it is the multiplicative form of flux linkage and currents. This is the per unit torque. This is the per unit flux linkage in the Q axis for the rotor, per unit current for the D axis rotor, and similarly these are the flux linkage and currents in the respective axis for the rotor. Why we are doing it? Because ultimately these TE would be used up by this equation of motion for the induction machine. So similar to the synchronous machine, we can write the swing equation over here again. So if you remember, it was J d square theta by dt square, something like that, Tm minus Te. This is for the synchronous machine. It was for synchronous generator actually. So mechanical torque was the input, electrical torque was the output. Now this same thing can be simply written as d omega by dt, again for the synchronous generator. Now for induction motor, what we can do, we can simply write j d omega by dt. Now the torque terms would be reversed, their roles will be reversed. So you can see that now electrical input would be required, so the electrical power input would be required, and mechanical torque would be the output. So the signs would be reversed accordingly. So this is what it is, what is written over here actually, where this is small m again for the mechanical quantities. And all we know what is the relationship between the mechanical quantity and the electrical quantity, and they are related by the pole pair p by 2. Now this is actually in actual quantities, because you can clearly see that this Te is a small letter, Tm is a small letter. So means this torque, Te, electrical torque, and Tm, the mechanical torque, all these are in actual quantities. So if you want to take all of them in per units, per unitized form, so you have to divide by the base power, and base power S base is 2 over Pt base omega base. This relation can be established. This is not a straightforward relation, but it could be established quite easily. If you go to the base quantity slide number 14, then you can see that S base and T base, they are related. They can be related with the help of the replacement of this. Either you replace V base by the lambda base here, V base equals lambda base omega base, or you replace lambda base here by V base omega base. Then you can clearly relate S base and T base. Okay. So using these three equation, this lambda base equals V base over omega base, and S base and T base equals to this, you simply use these three and you can come up with the one mentioned here, S base equals 2 by P, T base omega base. So once you divide by these S base, that is the apparent power base, on both sides, then you get this. There are some manipulations. Intentionally, we have included some omega base here and there, so that ultimately we can get this term half j omega square. Half j omega square. What is that? Half j omega square is nothing but the kinetic energy. The kinetic energy, half j omega base square. It is equivalent to half mv squared for linear motion. Okay, this is for angular motion on a body. So just to introduce this half j omega squared, we actually did this kind of thing, similar kind of thing in the derivation of the synchronous machine. For the initial part, classical model development, we actually did this. I don't know whether you can recall it or not, but we did this. So similarly, we are bringing some additional omega base terms here and there, and we are using this 2 by Pt base omega base, because S base has been used as the base power. We have divided on both sides the whole expression, and then ultimately we also note that omega r is 2 by P omega m. Okay, omega r is 2 by P omega m. So with this we can easily write down this expression. This is between the relation between the electrical quantity and the mechanical quantity. So with this inclusion of these two, omega r equals 2 by P omega m, and this assumption h equals half j omega squared by S base, if we incorporate these two here in this equation, then you come up with the another state equation. Now it is in terms of omega r per unit. Okay. If you don't want omega r to be your state variable, then you can also go for the slip to be one of your state variables. So in that case, you simply replace omega r by S. And of course, you should know what is the relation between S and omega r in per unit. Okay, so they have a negative relation. Omega r per unit and S, they have simply they have a negative relationship. Why? Because if you see S is what? Omega base minus omega r. If you take in per unit, you divide by omega base. So what do you get? So if you take ds over dt, then what do you get? You have to take d by dt of this. So that means minus d omega r per unit over dt, something like that. So you see that there's a negative sign that relates the change of slip with the change of omega r per unit. So this is why you can see that if you switch from omega r expression to the slip expression, you have an additional minus sign. Okay. However, you can erase, you can get rid of this minus sign simply by writing twice h ds over dt is simply tm minus t. Just you swap these two and you can get rid of that minus sign that is appearing at the beginning. So either you can take the slip as your state variable, or you can remain satisfied with the omega r per unit as your state variable. No problem. You can go in either way. So then we have some algebraic expressions or algebraic relation. Remember, we are still bothered about the presence of IDS and IQS. Okay, those are still not our state variables. Our state variables are Vd dash, Vq dash, slip, or omega r. These are the state variables. So to help out with the presence of IDS and IQS, let's see how we can use up the algebraic relationships. So now from 14C, so what is 14C? Let's see. Let's go back to 14C. So 14C is this, psi ds and psi qs. So from these two, what we can do, let's see. So psi ds is simply, this part is nothing but, this first part is nothing but the repetition of 14C. And then from here, we simply have gotten rid of the brackets. We have expanded it. This is the expanded form. And then there is some grouping because you can see IDS there and IDS there. So after the grouping for IDS, you get XS minus XM square over XR. And if you can remember, this is nothing but your XS dash. So you have got psi ds equals XS dash IDS plus VQ dash. What's the benefit here? The benefit is that now psi ds can be replaced by the VQ dash, which is the state variable. Similarly, from 14D, which is the expression of psi QS, which is up to this point. Again, we expand this term. We get this term and this term. Again, we group this term and this term. Again, we find XS minus XM square over XR. So that is XS dash IQS minus VD dash. Again, by doing this, what we can do, we can simply relate the flux linkage, stator flux linkage in the Q axis with the corresponding state variable VD dash. Okay, now let's move further from 13A. So what is in 13A? So in 13A, we have the simplified expressions for VDS and VQS after we neglected the fast stator transients. So you only have two elements on the right hand side for VDS and another two elements on the right hand side for VQS. So, and specifically we have psi QS and psi DS on the right hand side. So from 13A and 13B, simply what we do, so this part is the same as 13A repeated here, and then psi QS is actually replaced by this XS dash minus XS dash IQS plus VD dash. From 13B, this is 13B up to this point. Then you replace psi DS by this XS dash IDS plus VQ dash. So you have got equation 18 and 19 developed. Now again, VDS is still, we have some currents IDS, IQS, and VD dash. Inside VQS, you have some currents IQS, IDS, and VQ dash. However, VD dash and VQ dash are state variables. So now we will try to get rid of those IDS and IQS by the help of some phasor, by establishing some phasor relationships between the voltages and currents. So let's see how we can do that. We start with the three-phase stator voltage expressions, any balanced system. So phase A is simply omega st plus some phase shift alpha, square root of 2 into Vt, where Vt is the RMS square root. If you multiply it, we get the peak value. Similarly for phase B and similarly for phase C. So the balance, being a balanced system, we have 120-degree shift from each other. Then we apply the Parks transformation for this ABC frame variable, which belongs to the stator circuit. And we also apply the per unitization, where the per unit terminal voltage Vt per unit is simply Vt actual divided by, because it belongs to the stator circuit, so we have to divide by the stator, V stator base. And the corresponding Vds and Vqs can be found simply by this Parks transformation. So which Parks transformation matrix should be used here? Remember, there are two. So which one should be used for this transformation?
Is TDQS.
Yes, TDQ0S, because clearly it is mentioned, it is a stator voltage. And you can also see the small s present there, representing these are stator quantities. So you should go for TDQ0S. Thank you. So now with that application, we can get the corresponding expression for VDS and VQS quite easily. That would be Vt per unit cosine alpha, where Vt per unit is this Vt over Vs base, and Vt per unit sine of alpha, where alpha is the phase shift, initial phase shift considered in the expression of the phase A voltage. So now we can take VDS, we can form this phasor VDS plus J VQS. So it would be Vt per unit cosine alpha plus J Vt per unit sine alpha. So when you take the Vt per unit common, you have cosine alpha plus J sine alpha, which is nothing but e to the power J alpha following the Euler's identity. That forms equation number 20. Similarly, you can do the same thing for the current. However, the current, of course, the phase angle would be a little different than the voltage phase angle. So intentionally, the phase angle is chosen to be a different sign, that is phi. So it would be IT per unit exponential of J phi, that is the current phasor in equation 21, and the voltage phasor in equation 20. Both belong to stator circuit. So you can call it like stator voltage phasor, and this is a stator current phasor. Now with all those calculated, we can now use equation 18, equation 19, and equation 20 to give us this circuit. Let's see how. So from equation 18 up to 20, we can actually form this VDS plus JVQS is Vt per unit exponential of J alpha. This is already available in equation number 18. Okay, sorry, equation number 20. So VDS plus JVQS equals to Vt e to the power J alpha. This is equation number 20. But we also have some VDS and VQS available in equation 18 and 19 in a different form. So you can see VDS and VQS. So what we can do, we can take RS IDS, whatever we have here, this plus J multiplied all of this. So while we do that, we can get this. So this term is nothing but your VDS taken from equation 18 plus J VQS taken from equation 19. And the whole thing is equals to Vt e to the power J alpha taken from equation 20. So thus we are actually using all three equations. And then we can group them, group the variables like Rs plus Jx s dash. Then you will see that we have this IDS plus JIQS common, plus you have Vd dash plus JVQ. Because of this J, it is JVQ dash, and the right hand side remains same. So this thing is nothing but the phasor expression for this circuit, a simplified electrical equivalent circuit for establishing the relationship between some internal voltage of a stator circuit, Vds and Vqs, and our state variables for the induction machine, that is Vd dash and Vq dash. And they are related by the help of the current IDS and IQs, and the stator coil resistance Rs, and the stator coil transient reactance Xs dash. So this is simply, if you apply now the KVL in this circuit, you can establish this. So this is nothing but the circuit representation of terminal voltage. Okay. So once we are done with this, now we are almost actually done with the modeling part of our induction machine, or especially the induction motor actually. So this is the complete dynamic algebraic equation. So DAE actually stands for dynamic algebraic equation model. That means this model involves some dynamic equations as well as some algebraic equations. Okay. So combinedly, they give the complete model for induction motor. So to start with, what is the first equation? This equation was actually discussed probably 2 classes ago. So let us try to recall it. This was the first equation mentioned in slide number 5. So you can see d theta r over dt is s omega s. Okay. So this was our first equation. So we are simply repeating it, but probably in a different form, a little different form, but the meaning remains same. So d theta r over dt is s omega s. This part is taken from equation number 1, and omega s is nothing but the omega synchronous, which is also the omega base. So then what we do, we simply take omega base on the left hand side, so it becomes 1 upon omega base d theta r over dt equals s, where s is simply omega base minus omega r by omega base. So this is your first dynamic equation. Next dynamic equation is associated with the rotor or the swing equation of the induction motor. So as I said, we can get rid of the minus sign that was appearing here on the left hand side, and we can make the right hand side look like Tm minus Te. So this is coming actually from the swing equation for the induction motor. This equation 22C and 22D, these are some transformed equations where actually we had some d psi r and d psi dr by dt and d psi qr by dt, but we took help of some simplifying notations, and accordingly we represented these two equations in terms of voltages. Okay, so those became actually Vd dash and Vq dash. And then we have the expression for Te. This Te is nothing but this psi qr idr minus psi dr iqr. This is one way to represent the electric torque, or you can also write it like Vqiq plus Vdid. This is another way you can write it. The same result you will get. So that means either you write in terms of purely some rotor quantities or purely some stator quantities. And then the last one is the another algebraic. So this is actually one algebraic equation, equation 22E, and another algebraic equation is equation 22F, which is the last one that we derived a few moments ago. So this is actually the complete dynamic algebraic equation that we may use for representing the three-phase induction machine type loads in our power system model for small disturbance stability analysis. Okay. Now the last question that remains after developing this model is, how do you initialize this? Any idea? Because it is a dynamic model and you have to set some initial equilibrium or initial steady state operating point. So for doing that, how should we proceed from here? Any help? How do you get the initial value of slip? or the initial value of theta r. So S0, theta r 0.
The first derivative is 0 ধরে
First derivative 0. Excellent. So this is one way to simplify the steps. So that means you get this equals to 0. So what do you get? Tm equals to Te. Okay, this is one outcome. Then what do you get? From here, d theta r by dt equals to s omega s. So s omega s equals to 0. Now where will you go from here? Okay, we just simply leave it here. Probably some more steps would be required for analyzing this S0 value. Now come to this. So you can take this equals to 0, because in a steady state, all the dynamic terms would be 0. Take this equals to 0. Okay, so in this manner, actually, you can simplify all the dynamic equations will actually ultimately result in some algebraic equations. Okay, and that would actually help you out in solving the initial value problem for this DAE system of equations. So there are some steps actually mentioned in the last few slides for this lecture. You can go through it. I will have a quick view of these, I should say. So let's go through it very quickly. We have to equate the left hand side. Okay, first. So these are the first steps, equation 22C and 22D. So C and D, because the left hand side contains some dynamic term, so you make it 0. This left hand side in 22D also contains some dynamic term, so make it 0. So those two are zeroed. So once you make them 0, then ultimately you will get some algebraic equations. Okay, so you get 2 algebraic equations. So those are done. Then what you can do, you can make them look like VD dash. You can see it is some VD dash. There is some VQ dash. So what you can do, you can take this remaining part to the other side, this remaining part to the other side, and then simply you can take whatever you have VD dash equals. So you will actually have some expression like VD dash equals something out of this, and from here VQ dash equals to something, okay, out of this. Then simply you calculate VD dash plus JVQ dash. You form this expression. So that means you take whatever you have here plus you multiply J into whatever you have here, and that would be coming here. So then you change the sides, and then ultimately you will have some 0 on the right hand side. Then you try to simplify the expressions, and ultimately you should come up with this kind of equation. VD dash plus JVQ dash equals some J multiplied by some terms, or also you have some J actually, and then this is IDS plus JIQS. And then from 22F, what else you can get from 22F? Let's see. From 22F, you see there's some other expressions of VDS plus JVQS where it is related to VD dash plus JVQ dash. So from there, you can write what is actually VD dash plus JVQ dash. So what would be VD dash plus JVQ dash? Simply you take this and bring everything else to the other side. So it would be VT per unit exponential J alpha minus this. Okay, so that would be your VD dash plus JVQ dash. So in that manner, you can get 2 different expressions for VD dash plus JVQ dash, one in 23A, another one from 23B. So once you get 2 different expressions for the same thing, then you can equate them. So then we equate them, and after continuation to few 1 or 2 steps, you will see that very nice expressions would come ultimately. So you will have VT per unit exponential of J alpha. You see some R plus J plus some J plus some other terms, and then the current phasor. So this is the voltage phasor. This is the current phasor. In between, you have some expressions. So in a sense, we can say that this is V equals some Z multiplied by some I. All are phasors. So that means this thing over here is nothing but some sort of impedance. Okay, we can call it like some sort of impedance representation. And if you revert it, instead of this expression, if you want the expression of the current, then simply you have to invert this, and then this one would be some sort of admittance. So you can say some I equals I into some Y, sorry, I equals to some Y and some V, where all of them are phasors. Okay. Why we need this instead of this? So there is some additional benefit. Let's see in the last slide. Okay. So those are actually the previous slide. We saw the relationship between the voltage, current, and impedance or admittance. I mean, either you can go for this I equals YV or V equals ZI. And along with that, you can also calculate the real power. Okay, what would be the real power? The real power is simply P is the real part of VI conjugate. So this V means it is a VT phasor, and this I means it is IT phasor. So you know what is your VT phasor, you know what is your IT phasor. If you take the conjugate, so you see for the conjugate term, you have a negative sign appearing in the angle. VT is not conjugated, so it is appearing as it is. So VT per unit e to the power j alpha multiplied by IT per unit e to the power minus j phi. The phase is actually inverted. And then you simply include all these expressions of VT per unit e to the power j alpha, IT per unit e to the power minus j phi. You include all the expressions, you come up with these big expressions over here. Equation number 25. So now equation 25 actually gives you the relationship between the real power PT, the numeric value. Remember, PT is not a phasor, it is a numeric value. So you don't see any J term, any complex term appearing here in this expression. All these are magnitudes. This S is not Laplace. This is the slip value, slip. Okay. So everything here are real in nature. So this is a real expression. There is no complex, this is not a complex expression, because actually you are looking for the real part of the complex expression. So ultimately whatever will come, it will be some real value, and VT square in per unit. So it is actually giving you the relationship between the real power and the terminal voltage. So now actually this equation 25 is a non-linear expression in terms of VT. Okay, it is not a linear expression because of the presence of this squared term. So when you solve the nonlinear equation, one of the characteristics of a nonlinear system is that you actually come up with more than one roots or multiple roots, okay, for the system. So accordingly, you have a second order system. It is a second order equation, VT square. Okay, it is a nonlinear equation in terms of VT square. So you have one equation for PT and VT square. You have another equation that we derived in slide 28, that is between IT phasor and VT phasor. So what you do the last three steps for finding out the solution for your system. That means the initial condition for your system. So what are the steps? After you derive all these equations, the steps are as follows. So assuming that you have some given values for PT, QT, and VT, all are in per unit, of course, and these values should be made available from the load flow analysis. So these are your operating conditions. PT should be known or given, QT should be known or given, VT should be known or given or calculated with the help of load flow analysis. In general, load flow analysis is done and you get the values for PT, QT, and VT at a certain bus. So let's say in a very big, in a power system, let's say this is your generator, transformer, transmission line, this is a bus, and at this bus, let's say you have induction motor. So by load flow analysis means that you are simply calculating what is the power that is being injected, real power, what is the terminal voltage, and what is the reactive power actually consumed by the induction motor. So PT, QT injected at this bus and VT at this bus in per unit magnitude. So all these three information, of course, could be achieved with the help of load flow analysis. So this is what is meant by this. And at the same time, slip S can be calculated or obtained. Once you know PT, QT, and VT, you can calculate the slip. Or slip could be one of the variables in your load flow solution. Okay, where you have induction motor, slip could be one of the unknown variables which need to be calculated. So once you solve the load flow analysis, the slip value will actually automatically result in. Then, because equation 25 is quadratic in nature, as I mentioned earlier, so it will give you actually two different solutions for S. Two different solutions for S. Now, which one you take? So one slip would be impractical. One of the values would be impractical. Let's say some negative value of slip. So if any negative slip comes, that means that would actually operate your machine as induction generator. So you will not go for that. Any slip value, so any slip which is positive, that means it is the induction motor mode. So you should go with that. Okay. So that means actually this S, probably I said something else. So this S actually can be obtained once you know PT, QT, and VT. So PT, QT would be some other expressions, of course. QT would be imaginary part of VT, IT conjugate phasor. So similarly, you will have some other expressions for QT, and you can use these three expressions, PT, QT, VT, to solve this quadratic equation. Okay. Ultimately, what you will get this slip. And because of this equation being quadratic in nature, you will get two different values of slip. One of those values would be practical, for applicable for induction motor. You will choose only that one and you drop the other one. There is an alternate manner. Alternately, what you can do, you can say, well, I choose a certain slip at a steady state. I choose a certain value of VT, terminal voltage, and then I will calculate PT and QT. So this is another way. So once you calculate these four things, okay, VT, S, PT, and QT, once you know or you calculate combinedly these four things, the remaining variables would automatically calculate it. The remaining quantities here could be automatically calculated. Okay. So you see, once you get IDS, IQS, you can calculate VD dash and VQ dash. S, if you know S, if you know IDS and IQS, then you should be able to calculate VD dash and VQ dash and so on. So this is how you can actually come up with the solution, the initial value solution for your induction machine modeling. Yeah. So in a way, probably this is the last class where I actually talked about some topics, and the last class, actually theoretically the last class should have been on Friday, but that could be taken as some question answering session or review of the topics. Okay, I'm not going to introduce anything new, because if I start something new, I'm afraid I won't be able to finish it in the remaining one class. Okay, so that's it actually for this course. So in summary, what we have covered, or what we could cover actually, if we start from the beginning, we covered the synchronous generator modeling. So in the synchronous machine part, we covered the synchronous generator in detail. Then we came up with the exciter model. Then we saw that, well, with the introduction of the exciter, we have some stability issue. So we try to design the PSS. And we found that, well, with the proper designing of PSS, we can get rid of the problem that gets introduced with the exciter, high gain exciter specifically. So this was one break there. After that break of PSS lecture, we actually shifted our focus a little bit. We shifted actually to some source end, that is the mechanical device modeling, like the governor and turbine model. So the turbine model, the governor model, and there was the break. And then we have actually covered the load model, that is the induction motor, 3-phase. So probably this is in short the topics that I covered in this lecture or in this course. So if you have any query, any question, you can come up on the Friday and we can have a discussion on that. Okay. Okay, any question for today's lecture, especially today's lecture?
No, sir.
No question. Okay then. So practically this is the last topic that I actually could cover in this course, but theoretically we have another class, and I would post the class link there, and I will be there. If you wish, you can come and we can have a discussion on any confusion that you have on the lectures or the topics that I have covered throughout the session. Okay.
Okay, sir.
Okay, so thank you everyone, and thank you very much for taking the course, and our evolution still remains. So I have already posted the assignment number 3, and the deadline for assignment number 2 is also posted. So I would again request all of you to submit the assignments in due time. All the 3 assignments would be actually be part of your evaluation. Okay, so instead of the quiz, the assignments will be there. And in the final exam, besides the final written exam, as per the rule of IUT, we will also have a viva. So your final evaluation would be the assignments, the attendance, the final viva, the mid. So viva would take place at some time after the final exam, and then you have the final written exam. So this is in total the breakdown of your final evaluation for this course. Okay. Okay, so let's.
Sir, is
yeah.
there any deadline for the third assignment?
Yeah, third assignment I would post once the final exam routine is finalized. Okay. So I wish to make it probably on that day, or maybe 1 or 2 days after, 1 or 2 days after that. Okay, once all of your exams are done, probably then I will give the date accordingly. So for the time being, it is open. Okay, no due date is there. But actually for the practice of your exam, it is better to practice the problem that is given in the assignment. That would actually help for preparing your final exam. Okay.
Okay, sir.
Okay, so thank you all, and see you inshallah on Friday. Assalamu alaikum.